Yeah, so thank you. Sorry, just to confirm, I have till I guess for 1 hour. Sorry.
Yes.
Okay.
Yes.
Just making sure. Forgot for a second. Okay. So thank you. So so in the previous lecture, I sort of ended with the definition of the synthomic complexes. So via this sort of mapping fiber construction, using the divided Frobenius on the Nygaard filtered sort of pieces of the breakers and twists of the prismatic complexes. And so right. So again, the idea was that you have this sort of very explicit two-term complex for a quasi-regular semi-perfectoid ring. Then by descent, by sort of general descent theory, it formally extends to the entire quasi-synthomic site. And then, as so briefly at the very end, I mentioned that, as it came up in the questions, that you can actually extend it by animation to all p-complete animated rings. I actually will not go into so much detail of that now, because in talks I want to anyway focus on the quasi-synthomic case. But so I refer, for example, to the work of Bhatt and Lurie, absolute prismatic homology, for a detailed account of this construction. Okay, so I want to say a little bit more of how one actually accesses these objects. So I just sort of defined, to have stated some definitions, but I didn't want to be a little bit more concrete. And essentially, there's a key tool that lets one sort of write down classes in the synthomic complex. And this tool is studied quite a bit in the work of Bhatt and Lurie, and maybe sort of implicitly in the work of Bhatt-Morrow-Scholze. So there's the following basic construction that lets you sort of write down classes in the synthomic complexes, and it's a construction called the prismatic logarithm. So let R be in QR S perft. So then there is a natural map called the prismatic logarithm. And in fact, there's a version of this construction also makes sense for any prism. So there's a map called the map of abelian groups called the prismatic logarithm. And it goes from the Tate module of the units in R into prism of R twisted by 1. So it's a map of abelian groups. The left-hand side is just an abelian group. And this map has the property that its image is exactly the fixed points of phi1. Fixed by the operator phi1, which again has sort of a pole. And so in fact, this establishes an isomorphism between the Tate module of the units in R. And so in particular, it's landing in these fixed points, which means it's landing in the first synthomic complex. And so this gives an isomorphism between the Tate module of R cross and the synthomic complex with weight 1 of R. Okay. So this is the sort of the basic tool of actually writing down classes in synthomic complex in the synthomic complexes, which is that they're coming from the units in
Akhil, could you stop for a second? We have some technical issues here.
I think there's also a question.
There is a question from August.
From Arthur August.
Arthur?
Sorry. This is my typical question. Can you explicitly define that map log prism? It looks like very nice.
Well, sorry. So I mean that also involves explicitly defining the right-hand side, this breakers and twist by 1.
Right.
We're not going to get into the details, but let me just refer. There's a really nice account of this in section 2 of the APC paper. So for any prism, sorry, maybe you can see this if there's a technical issue. Okay, so
no, it's solved.
Okay, so for any prism A comma I, they write down a map from the rank 1 elements in 1 plus I, so those elements where delta is 0, to A twisted by 1. And so they, in particular, they write down a definition of this A twisted by 1, and they somehow write down this map. So pretty explicitly. And so if you have an element of TP of R cross, then you can produce a rank 1 element in 1 plus I inside prism of R, and then you have this map. So this is section 2 of APC, and I also refer to Drinfeld's papers, where Drinfeld has a construction, has essentially equivalent construction of this Borel and twist, and this map using the Stacky formalism.
Thank you.
Okay. Okay, so in particular, so this gives you some sort of explicit way of writing down classes in weight 1, and then in general, you can sort of take products to write down classes in general. Okay. So this is sort of what I wanted to say about the Syntomic homology of p-adic formal schemes, that it's defined as these filtered Frobenius eigenspaces of prismatic homology. The next thing I wanted to explain is the comparison with Atoll cohomology. And this is important if you want to define the Syntomic homology of an arbitrary scheme and not only of a formal scheme. Okay, so there's a following theorem, which is, so this is in the Bhatt-Morrow paper. It was also observed in Morrow. And it states that if you have any p-adic formal scheme, there is a natural multiplicative map which goes from the direct sum of zp of I of x, so as defined above, well, let's say if x is quasi-synthomic, to the usual Atoll cohomology of the generic fiber. And we could say I and z, and this is the usual Atoll cohomology of the generic fiber. So this is the analog of the period map in the Fontaine-Messing and Kato theory from syntomic complexes to Atoll cohomology of the generic fiber. Right. And the idea is that this map is very canonical, and you can sort of define it by descent. And so let me just sort of sketch the proof. So proof sketch. So consider the case where X is spoof of OC. For C, an algebraically closed non-Archimedean field, complete non-Archimedean field of mixed characteristic, and OC is the ring of integers. So in that case, you can compute, so this is sort of the essential case that you have to consider. And in that case, both sides are polynomial algebras on a class in degree 1. Well, for example, that comes from the system of p power roots of unity. If you choose a system of p power roots of unity, 1 zeta p squared, ... that gives you, so by this prismatic logarithm, that's going to produce a map in H0 sin of ZP of 1 of OC. And similarly, by Kummer theory, it'll produce a corresponding class in ZP of 1, the usual Atoll cohomology of the generic fiber. And essentially, there's a unique map that carries the first class to the second class, and then because both sides are polynomial algebras on these classes, that gives you a unique map of graded rings. So essentially, you reduce to this case where it's X is spoof OC, and both sides are polynomial algebras in the corresponding classes into group 1, and they're both sort of defined in the same way, and so you have the map. And then this is also going to extend to spoof of a product of rings that look like OC, because in this case, both sides are going to commute with products in this case, and so you would have such a map. And then you can reduce to this case by descent, and then you can reduce to this case by arc descent of the right-hand side. So essentially, there's a unique sort of canonical map that that you can define from the synthomic complexes of a p-adic formal scheme to the Atoll cohomology of the generic fiber, and it's determined by the fact that the right-hand side is an arc sheaf, arc p sheaf. So, and that lets you somehow reduce it to like products of valuation rings of this form. And then you essentially just have to normalize what happens in degree 1, and you choose that normalization using the prismatic logarithm, which is giving you a way of producing classes in ZP of 1 of X, and the usual Kummer map, which will produce maps in ZP of 1 of the generic fiber. So this produces such a comparison, and again, this is explained in the APC paper. So let me just say, so this is explained in the APC paper. And then as a result, you can define the synthomic complex of any scheme.
Akhil, when you say APC paper, it's almost absolute prismatic homology.
Sorry, yes. I should, thank you. So Bhatt-Morrow-Scholze, absolute prismatic homology. Okay. Yeah, so anyway, just to explain that there's sort of a canonical way of producing this comparison map from synthomic complexes to Atoll cohomology of the generic fiber. And as a result, you can define synthomic complexes of any scheme. And let me just say it's affine for simplicity, and then you can define it by Zariski descent. So namely, the synthomic homology of A is going to fit into a pullback, where you have the synthomic ZP of I of A, where you have ZP of I of, well, technically I should say the derived P completion of A. So this is now a P-complete object. So this is something that fits into the previous formalism. ZP of I of A adjoin 1 over P. This is the usual Atoll cohomology of A, where you've inverted P. And this maps to ZP of I of A P completed invert P. Again, that's the Atoll cohomology of this ring. And then you have this bottom horizontal map by the above construction. So by the theorem I just did above, you have a canonical sort of bottom horizontal map. And then you define ZP of I of A so that you have a pullback like this. So then by Zariski descent, you get a definition of synthomic complexes for an arbitrary scheme. Yeah, so also in this theory, so maybe I should first sort of give some examples before I continue. So this gives us a definition of synthomic homology, or of the Z mod P to the n twisted by I sub x. And let me write down some examples. So the first example is that ZP0 of x is the Atoll cohomology, or pro-Atoll cohomology of x with ZP coefficients. And this is just a constant sheaf ZP. So in weight 0, it's usual pro-Atoll cohomology. Next example is that ZP of 1 of x is always, well, you take the Atoll cohomology of x with coefficients in Gn, shift by -1, and P complete. So ZP of 1, I mean, this is again sort of something that happens in motivic homology. Weight 1 motivic homology is always in terms of GM. And here you take the Atoll cohomology of GM, with a shift, and take the P completion. And this, right, so this fact is coming from the prismatic logarithm. This is via, well, for p-adic formal schemes, this is via the prismatic logarithm. Right. So another example, I guess I should state this explicitly for formal schemes. Right. So ZP of I agrees with the Fontaine-Messing / Kato definition for I less than or equal to p minus 2, or for all I up to isogeny. So this was the earlier definition using the Theorem complex or the Hodge filtration. And right, so this is in work with Antio, Bhatt-Morrow, and Nicolas. Another feature is that, right, so as I mentioned, the ZP of I's is supposed to be some analog of motivic homology. And so this is proved in, again, in the APC, the Bhatt-Morrow paper, which is that the ZP of I, they satisfy a lot of the things that you would expect from motivic homology. For example, they satisfy a projective bundle formula. And there's a theory of turn classes. And again, the idea is that the ith turn class is going to live in ZP of I, in H2I of ZP of I. And this is all, everything is somehow, everything, well, this sort of gets built up from the case of weight 1 and using the prismatic logarithm. Okay. Okay. So I think it's, kind of an interesting problem to sort of compute more examples of these ZP of I's. And what I wanted to explain in these lectures was a description of the syntomic complexes for regular schemes. So the goal of these lectures is to describe describe the syntomic complexes of regular schemes. Right, and so in equal characteristic, this is this is in BMS2, and I mentioned it earlier. So if X is a regular FP scheme, so let me switch from the ZP of I notation to the Z mod P to the N, the mod P to the N notation. Then Z mod P to the N twisted by I sub X is exactly this Wn omega I log X shifted by minus I. So in equal characteristic, there's this description of the syntomic complexes. And I wanted to describe somehow an analog for in mixed characteristic. So suppose that X is a regular p-torsion-free scheme. And let's say that we want to describe Z mod P to the N twisted by I sub X as an object of the derived category of Atoll sheaves of X with Z mod P to the N coefficients. So what can we say about it? Well, first of all, if we restrict to the locus where if we restrict to the locus where P is invertible, we're always getting the usual tape twists. So if J from X adjoin 1 over P to X is the open inclusion, then J upper star of Z mod P to the N twisted by I sub X is always mu P to the N tensor I. So we obtain a comparison map. Which goes from Z mod P to the N twisted by I sub X to RJ lower star of mu P to the N tensor I. So we always have a comparison map from the generic fiber like this. And well, there's the following fact, there's the following additional fact. So this is proved in the article with Antio, Morrow, and Nicolas, which is that the left-hand side is always in cohomological degrees at most I. So the synthomic complexes, if you think of them as objects of the derived category of Atoll sheaves, they always live in degrees at most I. And so the above comparison is actually going to lift to the truncation. So Z mod P to the n twisted by I sub x, mapping to tau less than or equal to I of Rj lower star mu P to the n tensor I. So I think there's a question.
Okay, so this bounded less than or equal to I, which is like for motivic homology, is it you prove it for regular thing, or this is as a general fact on this for everything for these synthomic complexes?
Oh, thank you. This is true in general. This is not specific to regularity. In fact, so these synthomic complexes are going to be left con-extended from smooth algebras, not quite animated as in polynomial algebras, but they're left con-extended from smooth algebras. So these kinds of bounds, they actually reduce to that particular case. So yeah, so this is true for all x. Yeah, but and in particular, you have this comparison map as well for all x. But I guess the statement about it is specific to the case where x is regular. And so so there's the following theorem. So this was proved in my article with Bhatt. Yeah, so let me give this a name. Let me call this star. So the comparison map star it's an isomorphism in cohomological degrees at most I. Sorry, it's an isomorphism in degrees less than I. And in degree I is an injection. So if I tell you this, that means I've completely described this object Z mod P to the n twisted by I sub x as an object of the derived category once I've told you what the image in that top cohomological degree is. So let me also tell you that. So the image in the top cohomological degree is precisely the image of the symbol map from OX cross tensor I into Rij lower star of mu P to the n tensor I. Sorry, so here you have there's a Kummer map which goes from OX cross to, well, even OX adjoin 1 over P cross into R1 J lower star of mu P coming from the Kummer sequence, and then sort of take the you can take the I's tensor power of that, and you get this sort of symbol map. And the claim is that's exactly what this map star is doing on cohomological degree. And so roughly heuristically, the reason for that is that if you have a local unit on X, then that defines a class in H1 synthomic. And so if you can sort of cut them together and define classes in HI of weight I synthomic. And then the fact is that those HI of weight I are all sort of generated by symbols. So the direct sum of HI of Z mod P to the n, so I sub x, is generated in degree 1. And in degree 1, we have the map from OX cross. Which comes from the fact that synthomic cohomology in weight 1 is essentially the cohomology of Gn with the shift. Yeah, so maybe I should also say that there's this object right here is studied as essentially some form of a Miller K theory, and it's studied in an article by Luders and Moron. Okay. Sorry. So just to reiterate, the statement is that this comparison map from the synthomic complex on X to this truncated Rj lower star of mu p to the n tensor I. So this is a map that you always have for any X. And the statement is that, sorry, if X is regular and p-torsion free, then this map is an isomorphism in cohomological degrees less than I. And in degree I, the image is exactly what you get from generation in degree 1 by simples. So it's the image of this sort of symbol map. Okay, so this is the statement of the theorem that I just wanted to explain a bit. Yeah, so let me write. So when X is smooth or semi-stable over DVR, this is generalizing the results that I mentioned earlier. So this is generalizing the results of Kurihara, Kato, Tsuji, and Koldmas-Niziol. Yeah, so let me also mention that this construction of the right-hand side somehow, where you take like these p-adic nearby cycles and modify them in the top degree. This construction of the right-hand side, so modified tau less than or equal to I, Rj lower star mu p to the n tensor I. It originally appears in work of Schneider in the case of a smooth scheme over a DVR. It was connected explicitly with motivic homology, again, in this case of smooth over a DVR by Geisser. And it was extended to the semi-stable case by Sato. And yeah, so this theorem is saying that the construction of the synthomic complexes from BMS2 and APC is recovering this construction in the case of and more generally something like it for regular p-torsion free schemes. Yeah, so okay, so that's a statement. Try to explain some ingredients of the proof, but maybe let me just mention sort of a couple of questions that might be interesting. So questions. Right. So the first question is so the idea, as I mentioned, is that these synthomic complexes are supposed to be some sort of étale version of motivic complexes, and at least to my knowledge, right now, the theory of motivic homology has not yet quite been developed in the generality of regular schemes, but it would be nice to, for example, have like an actual theory of motivic homology for regular schemes, such that you could recover this construction using well, p-adic étale sheafification. So do the synthomic complexes of regular schemes actually arise as p-adic étale sheafifications of sort of actual motivic complexes? And if so, is there an analog of this sort of description of the synthomic complexes? Is there some sort of description like that of the mod p motivic complexes? So yeah, so this question in the semi-stable case is essentially it's mentioned in the article of Sato. And it's essentially done, and it's proved in the article of Geisser if for something that's smooth over a DVR. But so one could ask this for more general sort of regular scheme. Right, so another general question is, how can one compute synthomic, so in a slightly different direction? So this is giving an answer for regular schemes, but I think it's sort of an interesting question to try to compute these synthomic complexes for singular schemes. In particular in mixed characteristic. And let me just mention that there's this work in progress of Antio, Krause, and Nikolaus for the synthomic complexes. So there's a research announcement on the archive. Of the rings Z mod P to the N. So in general, this will also be presumably a harder question in mixed characteristic than an equal characteristic. And one motivation for them was the synthomic complexes of Z mod P to the N are closely related to the K theory of Z mod P to the N, which has been sort of a long-standing open problem, a p-adic K theory of Z mod P to the N. Yeah, so they have some methods for studying the synthomic complexes in this case. Okay. Yeah, so I guess in this talk I wanted to explain some of the ingredients that go into the proof of this theorem that gives a description of the synthomic complexes of regular schemes. Right. So I guess let me start doing that. So essentially there's sort of two main ingredients that go into this argument. So two main ingredients for the proof. The first ingredient is the Atoll comparison theorem in prismatic homology, which has sort of a nice formulation in the language of Syntomic homology. And the second is this notion of F-smoothness that we explored a bit in our article. And this is essentially some analog of the Cartier isomorphism for smooth FP algebras for regular schemes in mixed characteristic. So I think I'll talk about, I was planning to talk about F-smoothness tomorrow. So for the rest of today, I wanted to talk about the Atoll comparison theorem in the context of Syntomic cohomology. Okay. Okay, so yeah, so the Atoll comparison theorem in this form, right? So essentially, this theorem is somehow about the relation between the synthomic cohomology of a regular scheme and the synthomic cohomology of the generic fiber where you've inverted P, and sort of comparing them in some range of degrees. In fact, this Atoll comparison theorem gives you a way of comparing the synthomic cohomology of any scheme, let's say QCQS scheme, and the cohomology, the synthomic cohomology of the generic fiber, which is the Atoll cohomology of the generic fiber. So the idea is that the Atoll comparison theorem, it gives a way to compare synthomic cohomology of a scheme and its generic fiber, which is equivalent to the Atoll cohomology of the generic fiber. So let me formulate it. So let me formulate it now. So recall first that ZP of 1 of x is exactly, well, you take the Atoll cohomology of x with coefficients in Gn, shifted by -1 and P complete. So this is equivalently, it's the inverse limit of the flat cohomology of mu P to the N. So if your x is z adjoint zeta P to the infinity, where you have a canonical system of P power roots, you obtain a class epsilon in H0 of ZP of 1 of z adjoint zeta P to the infinity by choosing this compatible system of p power roots of unity. Right. And so now there's the following theorem. So theorem. So I guess this is due to Bhatt-Scholze. And in this form, due to Bhatt and Lurie. It states that if X is a QCQS scheme over Z adjoint zeta p to the infinity, then the map from the Syntomic Homology of X to the Atoll homology of the generic fiber, or equivalent the Syntomic homology of the generic fiber, it exhibits the target as the localization at epsilon in the p-complete sense. So it exhibits the target as the localization of the source at epsilon in the p-complete sense. Yeah, and so this is, well, this is somehow, this ends up being equivalent to the form, for example, in the Bhatt-Scholze article, because when you take the Syntomic homology of X and when you're inverting epsilon, this corresponds to, again, in the p-complete sense, you're taking the prismatic homology of X, you're inverting the prismatic ideal, and you're taking the Frobenius fixed points. So one can translate this, and I mean, this is explained in the Bhatt article, but essentially one translates this into the statement that's in the Bhatt-Scholze prisms and prismatic homology Atoll comparison theorem. But it sort of takes this nice form. The map from Syntomic homology of X to the Atoll homology of the generic fiber is given by inverting a class, again, in a p-complete sense. Now, right, and sorry. So I guess the point is that epsilon becomes invertible on the right-hand side because it's giving you a trivialization of ZP of 1 on the right-hand side. On the right-hand side, on the generic fiber, ZP of 1 is an invertible sheaf, and epsilon is a generator, since you're over Z adjoint zeta p to the infinity. But ZP of 1, the Syntomic complex ZP of 1 on X is not invertible anymore, so it gives some class that you have to invert. Okay, so this is what happens if you have a system of p power roots of unity. I guess in the article in our article we also extend this slightly to the case where X is an arbitrary QCQS scheme. So one can also extend an arbitrary and yeah, so essentially it's based on the following construction. So construction, there is a class V1, we call it V1 in the Syntomic homology of Z with weight p-1. So the class epsilon doesn't make sense over Z because we don't have a system of p power roots of unity. But the claim is that if you work mod p and you take the p-first power of epsilon, it actually makes sense over Z. So there is a class V1 in the Syntomic homology with weight p-1 of Z, which maps to epsilon to the p-1 in fp-1 of Z adjoint zeta p to the infinity. Right, so I guess equivalently, when you work on the generic fiber, mu p to the p-1 is trivialized, and that sort of lifting to a class which is no longer invertible in the Syntomic homology of weight p-1 of Z. So yeah, so you can construct V1 essentially by descent. from epsilon. I mean, essentially, or well, I should say epsilon to the p-1, because you can descend from z to z adjoint zeta p to the infinity, and you have epsilon to the p-1, and then you check that it's in the appropriate equalizer, and that lets you produce V1. So I would say a little bit more about V1, but let me just state the Atoll comparison theorem in this setting. So I guess essentially a corollary is that if X is any QCQS scheme, then the map from the Syntomic cohomology with mod p coefficients to the Atoll cohomology of the generic fiber exhibits a target as the localization at V1. And yeah, so you can essentially reduce this to the case the case where you're over z adjoint zeta p to the infinity. That's a formal argument, and then you obtain the statement. Yeah, so this is a statement that's useful for proving theorems like the one I mentioned above, because it gives you a very direct way of comparing Syntomic homology of X and the generic fiber, and then to prove something, somehow you have to identify V1 in prismatic homology. Okay, so I guess in the rest of today's talk, I wanted to, right, as I said, somehow to prove that, for example, this comparison map in the corollary is sort of close to being an equivalence, then the task one has to do is to sort of unwind where V1 is living in the prismatic homology, and really in the prismatic homology of ZP. And so in the rest of the talk, the rest of today's lecture, I wanted to explain a construction of V1 that's sort of purely prismatic, rather than by flat descent over ZP. So the rest of today describe V1, well, really the image of V1 in H0 of FP with weight p-1, not of Z, but of ZP. And right, so and this is some sort of Frobenius filtered Frobenius fixed points of the absolute prismatic homology of ZP. Okay, so first of all, what does it mean to give this class V1 in FP with weight p-1 of ZP? So by construction, it's enough to do the following. So it's enough to construct for every transversal prism A comma I. So transversal means A mod I is p-torsion free. It's enough to construct for every transversal prism A comma I the image of V1 in A, the image of V1 in A mod P Breakus and twisted by p-1, such that this image is a fixed point for the p-first divided Frobenius. And right, so we have this class V1, which in particular maps to the absolute prismatic homology of ZP, and with mod P coefficients. And that means whenever we have a prism A comma I, which I assume is a transversal prism, then that should give a class in A mod P with, or A twisted by p-1 mod P. So, and this should be completely natural in the choice of transversal prism A comma I. And to give such a choice is exactly the same thing as giving a class in the mod P prismatic homology of ZP. So, okay, and this is kind of a fun construction. You can it's saying that, yeah, you can sort of construct it for free, essentially. Okay, so what is V1 in A mod P twisted by P minus 1? Well, let me construct it by as follows. So first of all, choose a generator. So this module A twisted by 1, it's an invertible module over A. And let me choose a generator, which I can do sort of at least risky locally, which I'll call Y1. At least it's going to exist locally. And then the point is that we'll define V1 in terms of Y1, and it will be, and then check that it's independent of the choice of Y1. And that means it actually is defined globally and sort of loops. Okay, so we have the map phi1, which is going from A twisted by 1 to I inverse times A twisted by 1. We have this sort of meromorphic Frobenius on the prism A. And well, we can apply it to Y1, and we can consider Y1 divided by phi of yeah, so we can consider Y1 divided by phi of Y1. And this is a generator. So this is actually a generator. So this makes sense as an element of the ideal I, and it's a generator for the ideal I. Because phi1 is an isomorphism upon phi linearization. So we choose this element Y1, and which is a generator of A twisted by 1. We can take phi1 of Y1, which is now an I inverse times A twisted by 1. And we can form the quotient Y1 divided by phi1 of Y1, which is now living in the ideal I. And then so the definition is that V1 is going to be, well, first you take Y1 divided by phi1 of Y1. So that's again living in the ideal I. And then you multiply it by Y1 tensor P minus 1. And you take, so Y1 tensor P minus 1 lives in A twisted by P minus 1. And then, well, you reduce it mod P. So consider this as an element of A mod P twisted by P minus 1. So essentially the observation is that, well, because we're working mod P and mod P Fios of Frobenius, if you were to rescale Y1 by some unit, the choice of V1, it would sort of cancel, that rescaling would sort of cancel out. And so the choice of V1 is actually independent or the construction of V1 is actually independent of the choice of Y1. And that's essentially because phi1 is Frobenius semi-linear. And yeah, I guess you can also check for sort of the same reason that V1 is a fixed point for phi sub P minus 1, which again is phi1 tensor P minus 1. So this is going to, so for any transversal prism A comma I, this is naturally going to produce an element of A mod P or A twisted by P minus 1 mod P, which is a fixed point of the P minus first divided Frobenius. And it depends on this choice of Y1, which we can do Zariski locally, but it's going to be, if you rescale Y1, you'll get the same answer. So it will sort of exist globally. Okay. So now when you take the inverse limit over all transversal prisms, this is going to produce the desired class in H0 of Fp of P minus 1 with FCP. And yeah, so this is the desired class. And yeah, I guess you can. So this is, I guess, another way you can produce this class V1, and another way that you can, a different way that you could produce a class is to consider, is just define it by hand. Take this class epsilon over z adjoin zeta p to the infinity, and check that epsilon to the p minus 1 mod p sort of glues over the descent at. And that requires a little bit of sort of calculation with this prismatic logarithm, and I think it's roughly equivalent. Okay, I still have a few minutes left, so maybe let me just describe one other way to think about V1 in terms of the prismatic homology of ZP, because this is going to be useful for the next lecture. So one other way to sort of get a handle V1 is that, well, V1 defines a class in H0 of prism of ZP twisted by p minus 1 mod p. And this prismatic homology of ZP with mod p coefficients, there's a very nice description of the Nygaard pieces. It comes with the Nygaard filtration, and the associated gradients of the Nygaard filtration have sort of a nice description, and you can describe V1 in sort of up to filtration. And so actually this is sort of useful for the proof. So here, prism of ZP twisted by p minus 1 mod p carries the Nygaard filtration. And there's a nice description of the associated gradients of the Nygaard filtration. And so one has the following theorem. So so I guess this is explained in the Bhatt-Morrow article, for example. If you take the cohomology of the Nygaard pieces of the prismatic homology of ZP, and again work with mod p coefficients, well, this is going to be a bigraded ring, and it's a bigraded ring which is a tensor product of an exterior algebra on a class alpha with a polynomial ring on a class theta, so over Fp. Where alpha is living in homological degree 1 and internal grading p, and theta is living in homological degree 0 and internal grading p. So the cohomology of all the Nygaard pieces of the prismatic complex of ZP, it's a bigraded ring, and I'm writing the cohomological degree followed by the internal degree. Okay, so this is a description sort of up to graded pieces of the prismatic homology of ZP mod p, and this fact, I guess it's not so easy this fact is maybe not so easy to see if you think about the sort of site theoretic definition of the prismatic complexes via sort of quasi-synthomic descent. But this fact is explained in the Bhatt-Morrow article. It follows sort of more simply if you use the stack theoretic description. So this follows from the description of the Hodge-Tate stack of ZP in the article by Bhatt-Morrow. So essentially the point is, well, it's not quite this thing, but the Hodge-Tate cohomology, which this maps to, is the coherent cohomology of the Hodge-Tate stack. And that Hodge-Tate stack is essentially the classifying stack of this group GM sharp, the divided power envelope at 1 of GM. And then you can sort of do the computation directly on BGM sharp by identifying what quasi-coherent sheaves on BGM sharp look like. So this fact is it's maybe not so easy to think about if just in terms of this sort of site theoretic quasi-synthomic site description, because then if you want to define it for ZP, you have to involve some large ring and do some descent. it follows more simply from the Stacky approach to prismatic homology that is developed by Drinfeld and Bhatt-Morrow. But okay, so one has this description, and finally, let me just end by describing V1 up to filtration. So the fact is that V1 it's living in the prismatic homology of ZP. Well, there's a twist by p-1, but when you go to Nygaard pieces, that twist gets trivialized. And you can ask, where does it live in the Nygaard filtration and sort of what class detects it? And the fact is that this, well, since it's in the syntomic homology, it automatically lives in filtration at least p-1. And the fact is that this lifts to a class, which in the paper we call theta tilde, in n greater than or equal to p of the prismatic homology of ZP twisted by p-1. So it lifts to one higher filtration mod p. Well, it kind of has to, because the next, there's sort of nothing in filtrations from 0 up to p. And it's detected, so it lifts to filtration at least p, and then you could look at its map in GRP, and it's detected by the class theta in GRP. So yeah, so this is another way one can sort of get a handle on this class V1, which is that V1 is defining a class in the prismatic homology of ZP. And well, okay, so one could directly write it down in terms of prisms by sort of, so yeah, you can write it down directly for a prism, but you can also think about it in terms of, you can also sort of try to detect this class V1 in the Nygaard filtration on the prismatic homology of ZP. And then somehow the fact is that it's actually living in Nygaard filtration P and not in P+1, and you can detect it explicitly. It's a generator of, it maps to a generator of the P to Nygaard filtration. So yeah, so this vector is also useful in the proof of this theorem. So okay, so I'm a couple of minutes early, but I will stop now. So thank you very much.
Thank you, Akhil. Do we have questions from the audience? Yes.
Oh, it's a question about synthomic Z mod P and coefficients. So when you're over Fp, you have Milne duality for Wn omega I x shifted by minus I. So some kind of duality theorem for proper smooth schemes. And of course, if P is invertible, then you have the Poincaré duality. So in the general case, do you expect or not some duality theory, some trace map or thing which would somehow interpolate between characteristic P and characteristic 0?
Yeah, yeah, thank you for the question. Yeah, so sorry, so the question was about, right, duality theories for syntomic complexes. So I think, yeah, so I think the answer is that if you have for example, if you have something proper and regular over ZP, let's say flat, it's finite type assumptions, then I think there are supposed to be duality results between, well, it's going to be a little bit different in that it's going to be a duality between the syntomic complexes of X and the syntomic complexes supported on the special fiber. So these dualities are studied in the article by Sato. So let me just write. So Sato studies duality results for. Sorry, so maybe I should have said that. So Sato calls this construction, this modified like p-adic nearby cycles construction, Sato calls this p-adic Atoll tetras, and Sato proves some duality results for them. So p-adic Atoll tetras. And I think the duality is supposed to be between the, right, I think the duality is with the syntomic complexes and the syntomic complexes with supports on the special fiber. I think Bhatt and Lurie are also studying these dualities. So I'm not exactly sure if the statements of their result, but they're studying these dualities using, sorry, so I should have also said that the syntomic complexes are at least expected to be realized as the cohomology of a stack that Drinfeld has defined and called sigma double prime. And Bhatt and Lurie, I think, have been studying some of these duality results. And so we just refer to the ICN paper by Bhatt, where there are at least some of these duality statements are described on sigma double prime. And in particular, that should give you sort of these types of duality statements for Syntomic complexes. But yeah, so I'm not sure of exactly the exact statements here, but yeah, thanks for the question.
Okay, any other question? Okay, no question from Zoom. So thank you, Akhil, once more.